Okay, hey everybody, welcome to machine design. Here's the problem we're going to be working. I'm not going to draw this picture again, and I'm going to get rid of this image here, so go ahead and read the problem and write down the picture because you're going to need it to see where everything's coming from. But find the maximum internal pressure that can be applied to the pipe without exceeding the fracture toughness of the material. Whether the pipe will fail due to crack growth prior to permanently deforming. We're using Mill Handbook 5, which is a resource of material properties. I will be giving those so you don't have to have Mill Handbook 5. But yeah, just write down the values and kind of get this diagram drawn out. Alrighty, so starting with this problem. Since we're dealing with fracture, the base equation that we're going to have to use is Ki is equal to beta sigma square root of pi A. Okay. In this case, sigma is the stress intensity factor. And then sigma is whatever stress you want to use. Beta is a value we'll get from the chart. Excuse me. And A is the size of the crack. So going from there, though, we need to find stress in order to find out how long we can go before the thing will break, basically. So working within stress, we're going to recalculate this a little bit. Is equal to K IC all over beta square root of pi A. Now you see that I changed I to IC. IC is just more applicable to pressure vessels, which is the stress intensity, the stress concentration factors. I and IC are interchangeable very often, especially within these cases. Or you can call it I, whatever. It's kind of discretion. You just got to be careful that in other problems these two cannot be interchanged. But I and IC here, it's okay. Okay, so first we're going to find out, we need to find stress now in order to solve for the rest of this stuff because we're going to need beta and everything else. To get the stress, we know that it's a pressure vessel, but we need to find out if it's thick-walled or thick-walled. So in order to do that, you take the interior radius over the thickness, which in this case is 15 over 5, which is equal to 3. 3 is less than or equal to 20, so it's thick-walled. Thick-walled. And that tells you which equations to use. You can't use traditional thin-walled equations that are really super easy. You got to use a little more complicated ones. So in this case, the thick-walled equation, well, in every case, is equal to Ri squared times internal pressure all over R outer squared minus R inner squared times 1 plus R outer squared all over R inner squared. And there you go. So then, plugging in values here, we've got 15 squared times P. We can't solve for P yet because that's the thing we want to know. So, and then 20 squared minus 15 squared times 1 plus 20 squared over 15 squared. And that gives us 3.571 P. And we're just going to hold on to that. So that's equal to our stress, the stress that we can use. So we can actually go ahead and sub that back up here into this equation, and we will in just a second. But we also want to know beta. Beta is a value that you get from a chart within the book. This is the chart right here. You have to find basically the superposition situation that kind of relates to yours. So we have a crack inside of a pressure vessel that's thick-walled. So we need to find A over R outer minus R inner. That's what that says down there. I'm going to write it out here. So to do this, we're going to go ahead, R inner over R outer is equal to 0.75. We can do that calculation. A over R outer, oops, I'm going to change that subscript a little bit. R outer minus R inner is equal to 2 millimeters over 5 millimeters again, which is equal to 0.4. Sorry if I'm not showing all my units on all of these, but they cancel out every time, so it doesn't really matter. Okay, so then using these two values of R right here, so we have Ri over R outer, which is one of these lines. In this case, it's 0.75, so we're going to be using this line. And then we have A over R outer minus R inner as 0.4. So looking at 0.4 and 0.75, we're going to say that that gives us a beta equal to about 1.67. We're going to say 1.67. That's pretty close. There we go for that. So we've got our beta, we've got our sigma in relation to P, because we're trying to find the P, trying to find internal pressure. Is our question. Okay. Let's see here. Make sure I grabbed everything else. Oh, and we also need the stress intensity coefficient or factor. You can get that from Mill Handbook 5 or some other chart, depending on what you have available. But if you look in there, for 70, 75-T651 aluminum, and it's going to be plate. It's plate because a tank is always made from roll plate, so you can consider it a plate no matter what when you're looking at these values, looking at material properties. We're going to do it in the LT direction, which is just kind of a standard. So in this case, KIC is equal to 29 KSI square root inch, or 31.8 megapascals per square meter, or square root meter, times square root meter. And that's it. So now solving these in and putting them in the equation that we had started back up here, we have 3.571 P is equal to 31.8 MPa square root meter all over 1.67 KIC as the square root of pi times 0.002 meters, so that we keep the units straight. So this is our two, oh sorry. So these are 2 meters. So 31.8, so on and so forth, 1.6, and 0.02 meters. There we go. And if you solve that all out, then you get P is equal to 67.3 megapascal. And that's your answer for the first part. That's the maximum internal fracture that you can, or pressure you can have without having fracture, or until fracture, basically. So now, moving on, we need to check sigma to find out if it's going to fail next because of fracture or because of yield first. That's right, isn't it? Yes. Fail due to crack growth prior to permanently deforming. Okay, so basically, is it going to crack and break before it stretches? And if it stretches, then good. The tank is self-adjusting to increasing pressure, but if it breaks, then you have a tank failure. So we want it to fail due to yield first. But so we've got, I'm actually just going to start this on a fresh page. Let me throw it up here. Alright, so for part B, here, sigma is equal to 3.571 P. So we're back to P again. But we have just solved for the maximum P. So we use this maximum P here in order to find the maximum stress so that we can compare it to yield strength and fracture strength and so on and so forth, or fracture toughness. So this is equal to 3.57 times 67.3 megapascals, and this is all equal to 240 megapascals. Now, we're going to go sigma is less than SY. Right there, yes, and there's no factor of safety applied. So that's what we're going to be doing here. Sigma less than SY. If it is, then there's failure. So, which is equal to, I'm going to change this a little bit. 7 KSI equals 461 megapascals. This value is from Mill Handbook 5 and table 3.7.6.0 in Shigley's book for each one of these values. So, oh, excuse me. Make sure I straighten this out. Make sure I get this straight. Yeah. So since 67 is less than the strength of yield, 67.3, which is the sigma, or the pressure internal, which has KSI. So the crack, this is the, I'm sorry, I skipped this step for you. Basically, yes, this is the relation that we want. SY is equal to 67 KSI, which is also equal to, SY is equal to 67 KSI, which is also equal to 461 megapascals. So the SY we get the SY from the mill handbook, and then we use table 3.61 in order to continue with that. So if you look at those tables, you'll see where these values came from, but I'm not going to show that right now. So with this relation right here, since this is less than this value right here, the crack is going to grow before it yields. Grow before yield. So we'll have crack failure before yield, which is not something that you want in a tank. And that's kind of a quick version of doing the second part there. But if you go look at those tables and look up, oh, this is 2400 megapascals, I'm sorry, 240 megapascal. But yeah, go through here, look at the tables. You use Mill Handbook 5 for SY, Mill Handbook 5 for SY, and then table in the Shigley book, table 3.7.6.0 V1. And that will give you the values that you need over here, and you'll see where those values come from. Alrighty, there you go.